Hi, everybody. Now we're doing 1.6. So 1.6 is the subject of continuity. Continuity is very important in a function. Let me just pause here. Hold on a second. Give you 1 second, please. Let me just pause this. It basically means that a function is unbroken, no holes, jumps, gaps. For example, this guy over here is not continuous at that point right there because there's a hole. Here you see it goes there to there, it jumps. And there's a hole. Now, this one has a hole and there's no value at when x equals c1. This one does have a hole. This one does have a value when x is equal to c1, but the value isn't where it belongs. You know what I'm saying? So basically, continuous just means that you can trace along the curve, without lifting your pencil off the paper. That's kind of what it means for us. And in order to be continuous, the function has to be defined at that point. The limit has to exist, and the function value has to equal the limit value. Meaning to say, over here, the function value exists, but it's not equal to the limit because the limit value is up here where the rest of the curve is. The function is down there, so it's not continuous. Okay, let's look at some. Already, every polynomial is continuous. Let me actually, my picture is. Every polynomial is continuous. I'm going to get rid of my. No, I don't want to. I should put it over here. Put myself over here. There you go. Every polynomial is continuous for every real number, and every rational number. A rational number is when you have a polynomial on top and another polynomial on the bottom. So that's continuous as long as the bottom doesn't equal 0. So let's just see what we look here. So all of these, x squared minus 2x plus 3, that's a polynomial. X to the third minus x is a polynomial. X to the fourth minus 2x squared plus 1. These are all polynomials, and they're all continuous for all values. And as you can see, I could trace it without taking my pen off the paper. I could trace any one of these. Now these guys are also continuous because it's automatic. They're polynomials. They're automatically continuous for all values of x, for all real values of x. Alrighty. Now these guys are going to be continuous except where x equals 0, and this is except where x equals 1. And this is always, why am I saying 0 and 1? Because if the bottom of the fraction equals 0, that makes the function undefined. Everywhere else, it's going to be continuous, but not when x equals 0. This will be continuous everywhere else, but not where x equals 1. This one, the bottom never equals 0 because the square is always positive, or at least it's negative. Square is always greater than or equal to 0. So it's going to be 1 plus something. So the bottom is always going to be a positive number. It's never going to be 0. So C is going to be continuous everywhere. Well, let's just look at the graphs of these guys. So that's 1 over x. You notice when x equals 0, it goes up this way and it goes down that way, but it's not, these two parts, these two branches, if you will, are not connected. By the way, this is called a hyperbola, and you see the branches are not connected. Here we have a straight line, but when x equals 1, it's undefined. X minus 1 is undefined. And here we have, as I said, since the bottom never equals 0 of this fraction, it's just continuous all the way through. Continuous all the way through. Beautifully continuous. And this one will be this similar thing. It'll be continuous everywhere except for x equals 1. This is going to be continuous everywhere except for x equals 2. And this will be continuous everywhere because the bottom never equals 0. Already. Now, normally continuity, we define it on an open interval. For example, I believe that was part of our definition. Let's just go back and look at that. And you see, we defined it on an open interval. A, B was open. Now we're going to extend that to basically just the endpoints of the open interval. That's what I mean by closed interval. It's just a closed interval is just an open interval with endpoints on it. So now the thing is, when you have an endpoint, normally to be continuous, it has to be continuous from both directions. But there is no both directions. If you're on the endpoint, it can only come from one way, not from both ways. And that's it. That's all we're going to do. We're just going to say that to be continuous on an endpoint, as long as it's continuous on one side, then you're okay. So here, at this point, so here it goes on forever. This part is open. This part down there, well, it ends. I can't approach 3 from the right side. I can only approach it from the left side, and that's fine because it's an endpoint, and that's all you can approach it from. So we're good. All right. Now here we have 5 minus x, which is a polynomial, so it's continuous. Here we have x squared minus 1, which is a polynomial, so it's continuous. All I got to do is see that these two polynomials hook up. They connect to each other. If they do connect, then it's going to be continuous all the way through. If they don't connect, then it'll be partially continuous, but not, it'll be continuous like in pieces, but not the whole thing. Anyway, if you look at this, they do connect right there. When x equals 2, this is 5 minus 2, which is 3, and that's 4 minus 1, which is also 3. So they do connect when x equals 2, y equals 3, and these two, one is a straight line, the other one is kind of, this looks like a straight line, but it's actually part of a curve, part of a parabola. That's it. They connect, so good. And they connect at the endpoints. Even though I cannot approach this top point from the right, because there's nothing there, but I can approach it from the left. So I am extending my idea of continuity to an endpoint. That's basically what it means by closed interval. Alrighty. Now we have my favorite kind of function, a step function. As you know, it kind of looks like a staircase. An example of this function is called the greatest integer function. So this means the greatest integer that's less than or equal to x. So if x is equal to 2.5, y is equal to 2. If x is equal to 2 and 2.9, y is equal to 2. If x is equal to 2, y is equal to 2. As long as x is anywhere between 2 and 3, except 3. Once it hits 3, it jumps up. Like here, it's equal to 1. Anything between 1 and 2, the y value is going to be 1. If x is anything between 1 and 2, the y value will be 1, except when it actually equals 2, then it jumps up to the next guy. And this is called a step function. Step functions are good for, like, what's a good example of step function, by the way, would be postage. If a letter weighs a half an ounce or a quarter of an ounce or 9/10 of an ounce, it's one stamp. Once it hits an ounce, and then up to an ounce. Once it hits 1.1, once it's over an ounce, once it's 1.1 ounces, it becomes 2 stamps, and it stays 2 stamps, until x is equal to 2 ounces, and so on and so forth. That's the if you're going to graph up the number of stamps. So that's an example of a step function. Here we're looking at another example of a step function. So we have a company produces 10,000 units in an 8-hour shift. The fixed cost per shift amounts to 5,000, and the unit cost is $3. So we're going to use the greatest integer function. Using the greatest integer function, you can write the cost of producing X units as C cost equals 5,000 times 1 plus the greatest integer in x minus 1 over 10,000 plus 3x. Where they got that formula from, I honestly don't know. And well, obviously the 3x is the unit cost. The 5,000 is the is the fixed cost, and that's how this goes. This is kind of interesting. And here, if x is anything between 1 and 10,000, between 1 and 10,000, this whole thing is just going to knock down to 0. So once x goes higher than 10,000, then this is going to become 2 and 3 and so forth. Anyway, when you the first 8-hour shift, this is going to equal 0, because there's always going to be some fraction that's less than 1. So it's going to want to be 0, because x is between 1 and 10,000. And then in the next shift, when x is between 10,001 and 20,000, this is always going to be 1 point something. So it's going to so the greatest integer will knock it down to 1. And the third shift, and so on and so forth. So if you graph these, you get, so here it's going to be, if you notice, it's going to come out to 5,000 plus 3x. To the next shift, it's going to be 10,000 plus 3x, and so on and so forth. And that's the first shift, that's the second shift, and that's the third shift. And that's what, a little shifty, but that's, I see my joke there, but that's what it looks like. Okay, compound interest. Compound interest, when you get interest on the interest on the interest. So if interest is added to the account so that future interest is paid on previously earned interest, meaning you're earning interest on the interest, then the interest is said to be compounded. So if you have a deposit of 10,000 and it's made in an account that pays 6% interest, compounded quarterly, so because 6% is the annual interest rate, the quarterly rate is 1/4 because it's a quarter. The quarter means 3 months. Is 1/4 of 0.06, which is 0.015 or 1.5%. So you get 1.5% every 3 months, and the balances during the first 5 quarters winds up being first you have 10,000, and then the next you have 10,000 plus the interest, 0.015 times 10,000, which gives you a grand total of 10,150. And then the next quarter you get 15% of that previous balance. So now you're at 10,302. And then the next quarter is 0.05 times 10,302, so it becomes 10,456. The next quarter it's going to be the previous balance, 10,456.78, right, which I got from here, plus 15% of that balance, and that gives me 10,613.63. Now, if I just did straight interest, it would be 10,600. Because I compounded the interest, you get an extra $13. And like I say, you know, it all adds up. It all adds up. But I didn't raise the interest rate. I just it's interesting. Without raising the interest rate, just by compounding it, you wind up getting more money. Now, because there's a limit of how much money you can get. It's not like you can compound it quarterly, daily. You can compound it every second. It'll always be more, but it's not going to be infinitely more. It's gonna, you know, we'll balance. We'll, you know, reach points as high as it goes. Anyway, so here we have a graph of the balance of an account described above. So A represents the balance of the account. So it's going to be 10,000 times 1 plus 0.015, that's the interest rate, raised to the 4t power, or the greatest integer in 4t. T is the, A is discontinuous, so T could be 1/4, 1/2, 3/4, 5 quarters, and so on. And but if you graph it, you're going to have this, and then this, and then this, and then that, and then that. So it's not something where it's about. Whereas you don't get interest every second. You don't get another penny every second. It's you get it in every 3 months. You get a lump, and it's going to look like this, a step function. But like I say, it's going to grow faster than if it was just straight interest, because you get interest on the interest, and that makes it more money. And that really concludes the section. Continuity is a very, very important. It's not a long section, continuity, though it is a very, very important topic. And we're going to have some homework questions in continuity. I'm going to put the homework in Canvas, as I always do. And we'll see you guys next time. Let's see. Oh, great homework questions here. That's really good. And yeah, we're all doing good here. There you go. Look at this. Look at that. The next thing we're going to do after this, that's it for now. The next thing we're going to do after this is we're going to to chapter 2. That's going to be our next thing. I'm going to get into some serious calculus. Anyway, everybody, it's been loads of fun, and we'll see you next time. Bye from Hogwarts, everybody. Bye.